everyone is all set, no questions, then we will proceed. So think about your questions and ask them now.
Stop and just start asking a question by question.
Just a general question. On your sample questions that you send out,
Yeah.
a lot of questions are you go into detail and very specific, but in class you just either brush over, go surface level. So I was just wondering, like...
Those are vague terms. You have to have a specific question to get an answer. You have a specific question. Yes?
For glycolysis, you said like steps 1 through 6 is like the innovating step, or that's when you're creating, and then the steps 6 through. But if you look it up online, it says 5 through 10. So like
1 through 5 is.
No, I had on the previous lesson you said 1 through 6.
1 through 6.
Yeah, but you just said 1 through 5.
But
So is it 1 through 5 or 1 through 6?
what is the question?
So the generative for glycolysis, right? You said before.
When is the ATP invested?
Yes.
Yeah, an investment step. You just said 1 through 6. You just said 1 through 6, but then you just said 1 through 5.
That's not important. Where is it invested?
Professor, I'm about to geek out. What do you mean it's not important?
There are 2 steps in which ATP is invested. There's the step 1 and step 3. Now, how you define the
Wait, but
investment step?
it's not step 3, it's step 4.
Step 3.
How are you telling me, bro?
Because he said it, step 4 last
No
time.
investment. Now, where you draw the line for investment, you can draw it at step 3. You can draw it at step 4.
So is it investment steps 1 through 5 or 1 through 6?
Yes, sir. Step 1 and step 3.
No,
That's where it is invested.
but when's like the
There
period?
is no definition of a pathway. You define it your way.
All right, thank you, Professor.
Pathways have no definition. We define the pathway starting from here and ending here according to our convenience. If you define investment steps as step 1 and 3, then that is the investment step. Yes.
When can we expect the midterm to be uploaded?
Steps 7 and 10.
36 hours before the exam.
Make 2 equal.
So it's 12 months.
Steps 1 and 3.
And what about the seating arrangement?
I think that we have 2 rooms, this room and the 121. There are more seats in this room than the other one. So it will be in alphabetical order. I'll email you probably 1 E through M in one room in this room and the rest. Something like that.
Everybody's asking questions. I'm not going to sit in one
How you feeling? Is this on? Good luck, guys.
When you have a mutation moving a phosphate from one position to another, if people, those who are not interested, you can leave. If there is an enzyme that moves a phosphate from one position to another of a molecule, that does not require ATP. So the way all mutases work is that the enzyme comes with a phosphate. There is an amino acid at the active site that has a phosphate, and that is transferred to the new position of the substrate. So there will be an intermediate in which the substrate will have 2 phosphates at the old position and the new position. And the phosphate at the old position is then transferred back to the amino acid. So that's how all mutases work. The phosphate comes with the enzyme, and that is the one that is transferred, so no ATP is used for mutases. And that brings up another interesting point about all mutases. When scientists work with mutases in the lab, they often find that their enzyme gradually loses activity in the lab, not in the cell. So what happens in the lab is that the enzyme that comes with a phosphate gradually gets hydrolyzed, and if it loses that phosphate, then the enzyme becomes inactive. And so the enzyme, if you work in a lab with these mucases, you will find that the enzyme loses activity. One easy way to reconstitute that activity is to add a small amount of this diphosphate. For example, if you are transferring phosphate from position 1 to 6 of glucose, there will be an intermediate that will be glucose 1,6 bisphosphate. So if you make that molecule and add a tiny amount of it to your enzyme preparation, then your enzyme gains back activity again. And that is true for all mutases. They don't need ATP. The ATP comes with, the phosphate comes with the enzyme. All right. Any other questions?
Are we going to see chair structures on the exam?
Why not? Yes, the chair structures can be there. Our projections can be there. You don't need to memorize structures. The only structure we did was glucose. And glucose is easy to, yes? Glucose is easy to know because all the groups are equatorial in the beta, and only in the alpha is one axial OH. All the other groups are equatorial. Besides that, you can draw the chair structure for other glucose, other sugars. For example, the two sugars that I asked you to know about are mannose and galactose. If you know that mannose differs at position 2, so the OH will be opposite of glucose in axial position, or galactose at position 4. So glucose, beta glucose has all groups in equatorial position, and that is another reason why beta glucose is the most abundant in nature. If you have any epimer means change at one position. Mannose, for example, will have one extra OH group in axial position, so obviously that will be less stable. Or galactose will have one extra in axial position. So that's about the chair. So it's not anything more fancy than that. And of course, you need to know the linkages that we did, like alpha 1,4, beta 1,4, 1,6. What does alpha mean? Alpha means the carbon 1 OH is pointing down, is in axial position. That is alpha. If it is in equatorial position, that is the beta. And 1 to 4 means the linkage is to the carbon 4 OH of whatever sugar it is. If it is glucose, that of course will be in equatorial position. If it is galactose, that will be in axial position. So the first name, alpha, for example, alpha 1,4, let's say glucose. All right, so if you have the name glucose alpha 1,4 glucose, so this alpha refers to the first one. If you are drawing a Howard projection, so this alpha means the OH is pointing down. And it is going to carbon 4 of another glucose, which is this carbon. So you just draw another glucose here. And the fourth carbon OH is pointing down, so that means this will be pointing down. So this will be the alpha 1,4 glucose. If it was beta, then this O oxygen will be pointing up, and this whole ring will be above. Yes?
So when you say you want us to know like glucose, alpha 1,4 glucose, do you just want us to know what it looks like, or do you want us to know like what the disaccharide is called?
Both. What is it called?
That's not the...
All right, and what does it look like? It looks like this. So if this structure, you are not drawing anything, but the if this structure is given, you should be able to tell that this is a alpha 1,4 linkage, or what is a beta 1,6 linkage. So if the structure is given to you, you should be able to tell what linkage it is. Yes.
Yes, I just wanted to ask a question. On the quiz, you asked us to define what Km is.
Yes.
And I was looking at the notes, and you have it defined as Km equals 1/2 of Vmax.
No, Km is not Vmax. Vmax is a rate, Km is a concentration. Km is the concentration that gives 1/2 Vmax rate. Km is the concentration of the substrate that will give you half the Vmax rate. Km is not Vmax or half Vmax. Because Km unit is concentration unit and Vmax unit is rate unit. Yes. So there are other ways of defining Km. Like in Km you have half Vmax, so that means half of the enzyme molecules are bound to the substrate. So everything comes by logic. This is what Km is, that Km 50% of the enzyme molecules are bound to substrate, that's why it gives the 50% Vmax rate. Km is the usual concentration of most compounds in the cell. So concentration of most compounds will be somewhere around the Km value. The amount of substrate needed to get Vmax amount of rate will be about 10 times the Km approximately. So if Km is let's say 5, then it will take at least 50 millimolar to give you Vmax. And usually in the cell we never reach that high level. Alright, Km is also defined as the dissociation constant, which you can again define as a ratio of the products to reactants or as a ratio of the rate constants in the reverse and forward direction. So there are different ways of looking at Km. They are not that they are all different, but there are different ways of looking at it. Other questions? Yes?
One of your questions on the sample thing was, why do pK of free amino acids differ from those in protein?
pK of free amino acid is different from those in the enzyme. And why is that? Two things. No, what is your question? pK is different from enzyme, or pK of the two carboxyl groups are different? There are two different questions, right?
pK of free amino acids.
Free amino acid and in the enzyme. So in the enzyme it is a three-dimensional structure with other amino acids nearby. So if you have a enzyme that has many amino acids, and you are talking about a COOH here, the ionization of this COOH will also depend, other than depending on the amino acid itself, will also depend on what is here, what amino acid is here, or what amino acid is here. So if they are charged or not, if they are electronegative or not. So it may not be directly connected through sigma bonds, but spatially they are close, and that's why they can have an effect on the ionization of any amino acid. So pK of all amino acids will be actually very unpredictable in a protein. And there are examples, as I said, I gave you examples before, like histidine has a certain pK, and in the protein it may be totally different and leading you in the wrong direction. So it can be different because the local environment in three-dimensional structure may be different. In a free amino acid, we are always talking about free amino acid in water. If you have it in an organic solvent, then again pK will be different. So in water, the amino acid is surrounded only by water, whereas in the protein, it is surrounded by other amino acids which change the pK. As I said, there can be another question which you haven't asked, and that is, in any amino acid, why are the pKs of the two different? Like you have a side chain and a carboxyl group, so the pK of these two carboxyl groups are also different. This one has a lower pK always because the amino group always has a plus charge at neutral pH, and that plus charge is highly electronegative. Nitrogen is electronegative. Nitrogen with a positive charge is even more electronegative, and that pulls electron from this bond, right, and makes it a stronger acid. And because the alpha group is one carbon away, and this one is several carbons away from the nitrogen, the effect of this on this one is less than on the first one. All right, so that has the alpha one has always a lower pK than the side chain. Yes.
What's the difference between an apple enzyme and a hollow enzyme?
It's not just about enzyme, it's about any protein. When a protein doesn't have its cofactor, it's called an apoenzyme. Whatever cofactor that can be, like if you have an enzyme that uses, for example, FAD as a coenzyme. If the FAD is not there, then that's called an apoenzyme. And if the FAD is there, that is called an holoenzyme, HOLO. Same with other proteins like hemoglobin. If it doesn't have the heme, usually it doesn't, it's very tightly bound. So it doesn't apply to coenzymes or cofactors that are loosely bound because they always come and go. So the term is used only for those that are prosthetic groups, that means those that are tightly bound. For example, many enzymes have a vitamin B6, 3-deoxyl phosphate as a coenzyme, which is very tightly bound, never leaves. FAD is one that never leaves, but if it does leave, then that will be a coenzyme. The term is also used for example, lipoproteins. Lipoproteins, as we will study later, have lipids and proteins, but the protein is called the apolipoprotein. So we will study that later. Yes?
There was also another question on the quiz that was asking for the role of serine in a catalytic triad.
Right. The role of serine is so this is a OH, which is basically a alcohol. Alcohol has a pK around 15, 16. So that is very difficult to ionize under normal neutral conditions. So we will never find an alcohol that is ionized. That was a related question was about the tyrosine not acting as an acid-base catalyst because tyrosine is also an alcohol. It has a pK above 10. Not as high as 15 for aliphatic alcohol, but still high. So at neutral pH, these will never be as the negatively charged ion, but in a serine protease, this will be next to a histidine and then an aspartate. So the aspartate, this hydrogen bonds with the histidine, this hydrogen bonds with this one, so this hydrogen is eventually transferred between the histidine and serine. So there is a partial negative charge, so you have a hydrogen like this, so there is a partial negative charge on this oxygen. So that's how all these serine proteases work, by hydrogen bonding. The aspartate, which is already negatively charged, it's a carboxylic acid, is negatively charged. So that negative charge is partially transferred through the histidine to this serine. That means this hydrogen is partially removed from here, somewhere in between these two, by hydrogen bonding. So the serine has a negative charge, which makes it a strong nucleophile. Right. So strong bases are good nucleophiles. Hydroxide, methoxide, these are good nucleophiles. So serine with a negative charge will be a strong nucleophile, or serine with a partial negative charge will also be a strong nucleophile, and that is the one that reacts with the peptide bond and hydrolyzes it. Anyone else have any other questions?
So for the genesis, we were told that there's like a 6 ATP, but in the notes, there's like only 3 steps for ATP is like involved.
The first step in going in the opposite direction, gluconeogenesis. So you have to go from pyruvate to oxaloacetate and then to phosphoenol pyruvate. You need 1 ATP here and 1 ATP here. And you have to multiply these by 2 because these are 3 carbon and you are comparing for glucose. So 4 ATPs in this step only. 2 plus 2. Right, so that makes 4. And the other 2 are in the equilibrium step, 1,3 bisphosphoglycerate to 3-phosphoglycerate. So these are the 6 ATPs because you need to multiply everything by 3, sorry, by 2. And so there are 3, this one, and the bisphosphoglycerate, which is an equilibrium step. And multiply that by 2, that makes it 6. The other 2 steps in glycolysis, where you have glucose to glucose 6-phosphate and fructose 6-phosphate to fructose 1,6-bisphosphate. So these are the 2 steps in glycolysis where you have added ATP. Right, so those are the energy investment reactions. How you define this investment stage is up to you. The book define it up to 1 to 5 or 1 to 3 or 1 to 6. As long as the next ATP is not made, any of the steps can be put in this class or the other class. It doesn't really matter. It's a matter of convenience that we define pathways. But the investment phases are the investment steps are these, step 1 and step 3. So it is natural that one would expect that when you go in the reverse direction, if you are investing here, then in the reverse direction you should gain it. But the fact is that you don't gain ATP in these 2 steps because the reverse in gluconeogenesis will also be an irreversible step. So in both directions it is irreversible. In order to make it irreversible in this direction, you need energy so that phosphate is hydrolyzed to provide that energy. Alright, so whenever you have a regulated step and there is an opposite pathway, that regulated step will also be irreversible at exactly that same position. And you need to reciprocally regulate the pathways, which happens in this one. This is the committed step. So there is this fructose 2,6-bisphosphate. This is a compound made in small amounts that will regulate both these steps. It will inactivate one and activate the other. Now it's a question of memorizing which one is activated, which one is inactivated. I don't want you to memorize things, I want you to understand the concept. You can always look at a book and see which one is activated, which one is inactivated. One of them will be activated, the other one will be inactivated, and that has nothing to do with another pathway that is also reciprocally regulated by another molecule. So the fact that one is activated, the other is inactivated, that fact you need to know for all the reciprocally regulated steps. And also that if you are investing ATP in one direction, the other direction you are not going to get that ATP back because the other direction will also be irreversible and that needs to be hydrolyzed. So these 2 steps, you don't make ATP. So that's one important fact to remember, but this doesn't count in the 6 ATPs that are needed for pyruvate proteins. Alright, so that answers your question. Any other question?
Go over in what chemical form carbon dioxide is transported as hemoglobin and what conditions
I couldn't hear. What?
Like the last part of the first sample questions with what chemical form carbon dioxide is transported as hemoglobin, under what conditions does it, in the tissues does it react, and the percentages?
Under what condition carbon dioxide binds to hemoglobin?
Yeah.
So when there is more carbon dioxide like in the tissues, there is respiration and there is more carbon dioxide formed, and so it will dissolve in the water. So dissolving in the water is an equilibrium step. Water means the plasma, blood plasma. So it will dissolve in that to form bicarbonate. That is an equilibrium step. So that you can predict that where there is more carbon dioxide, more bicarbonate will be formed. For example, in the tissues, and when it goes to the lungs where there is less carbon dioxide than the tissues, then it will go in the reverse direction and carbon dioxide will be released and exhaled. If you are talking about carbon dioxide binding to hemoglobin, that reaction will happen only if the hemoglobin doesn't have oxygen. So the ideal the position for this to happen will be the tissues where the function of hemoglobin is to release the oxygen. So it releases the oxygen and then the carbon dioxide can react, not bind, just react with the N-terminal amino group and give you a carbamate, and that is transported to the lungs, where it will be in that the action will be reversed only if it binds to oxygen. So our binding of oxygen forces this one out, or you can say this one has to leave for oxygen to bind. Both of them cannot be bound at the same time. And that's why every carbon dioxide molecule that is transported from the tissues to the lungs in the form of a carbamate must be released. 100% of it must be released. Whereas bicarbonate, the majority of carbon dioxide is present in the bicarbonate, but majority of it stays there, it's not released. So only maybe 5% is released. All right, so whatever is binding, whatever extra amount is dissolving in the water, in the plasma, in the tissues, that is the amount that will be released. But the plasma already has 20 times more bicarbonate in it, and that always stays constant, whether it is in the tissues or lungs. So if you calculate the amounts, then 50% of the carbon dioxide that is exhaled came from the carbamate, and the other 50% came from the bicarbonate in the form of dissolved in the plasma. Is that your question? Or any other question? Yes.
How are Vmax, K2, and the modes of enzyme related?
What are the modes of enzyme?
Well, in the E plus S, it goes BS, and then it goes E plus P in that.
The modes of the enzyme are the ES. The different forms of enzyme, or
The modes or the molecules of the enzyme.
Oh, the
These are
mole.
your sample questions.
what does it say? Modes of enzyme?
Somebody asked him when he's going to
What is the question? Modes of enzyme.
Modes.
Or moles of enzyme.
Yeah, what about it?
And just to explain, how are Vmax, K2, and
Oh,
molecules?
so by definition, when you get Vmax? When you get Vmax when all the enzyme molecules are bound to the substrate. That is when you get the maximum activity, which means all molecules of enzyme are bound to the substrate. Right? So that means all 100% of the molecules in terms of moles will be bound to the substrate, and that gives you the Vmax rate. And by the same logic, Km means about 50% of it will be bound.
What about K2?
K2 is the rate determined step.
What about K2?
So how are K2 and Vmax related?
The Vmax, the K2 is the actual step that decides the rate. Right? The first one is a fast rate, K2 is the slower step. So that is the rate determining step and decides the rate of the reaction. So Vmax is determined by the K2 value. Yes, you have at the back.
I was saying, so Km is when, so Km is half Vmax.
Km is not half the Vmax.
I asked him already.
Vmax is a rate, Km is a concentration. Km is the concentration that gives you half the Vmax rate. Km is not Vmax or half Vmax. Km is the concentration that gives you half the maximum possible rate. So if this is a question in the quiz, which there was one of the sample quizzes, that option will be there. That's what is Km, half Vmax. That is not the right one. Km cannot be Vmax. Yes?
If on the test you give us like the Vmax and you have to calculate Km, since it's not like not an equation, kind of calculate for it or not?
There will be no calculation first of all, and so you are asking if Vmax is given, you have to calculate Km.
Yeah.
You cannot calculate Km if Vmax is given. They are two independent things. Km is the concentration, Vmax is the rate. If Vmax is given, you cannot really calculate the Km of it. And if one could be calculated from the other, then people wouldn't bother to find out both. right? We are spending so much of our time and energy figuring out what is the Km and what is the Vmax, equal to experiments to determine those. If one can be calculated from the other, then what's the point in determining them by experiment?
On a sample question, you told us to know what a beta mercaptoethanol is. What is that?
Beta mercaptoethanol. So we draw ethanol, CH2, CH2CH2OH. After the first CH2, we put a sulfur, that is SH. So that is beta mercaptoethanol. That means two carbon compounds with a SH group, which is a strong reducing agent. So the sulfide gels are a strong reducing agent. It's an artificial one, so it mimics the cysteine in the cell. There is also another one called dithiothiazole, which also has SH group. That's a reducing agent that biochemists often use in the lab. And of that, mercaptoethanol is a cheap one. You can really buy them in lots of malls. The people always use mercaptoethanol. So if you go to a biochemistry lab, the bad smell that you get from everyone working with anything is the mercaptoethanol. You have it in all their buffers.
Wait, what was the other one called? You said
It's called a dithiothiazole.
AP. What is it?
It's not in the, whatever we haven't done in the syllabus is not in the syllabus. But if you want to know, it's a dithiothiazole.
No, I don't want to know that.
It's basically that, just artificial. It's a, what did you say it was? It was a strong reducing agent?
What strong reducing agent?
Yeah, that's just.
So a reducing agent is what gives us
No, these are added to the buffer. These are in small amount, like millimolar concentration. They are added to all buffers so that it's a reducing environment.
No, indeed.
Otherwise, the cysteines will get oxidized easily. You don't want that. It blocks No, it doesn't block it. If any sulfur is oxidized by the oxygen, then it's converting back to the free SH. So that may be the active form of the enzyme to have the cysteine as SH. So this helps to keep all the cysteines as So mercaptoethanol is not a biological thing, it's an artificial chemical that Anything else? Yes.
Why is allosteric regulation faster than other forms of regulation?
Because binding is fast. Binding means two things have to come together by simple diffusion. Molecules move at a high rate, at very high speeds. So as soon as they come together, they will bind. And that's why there's a faster rate. So that's the rate of diffusion, which is, as you know, it's about 10 to the power 7 molecules per second. Yes. So that's a high rate, and so allosteric regulation is the fastest. Yes.
Is the main point of covalent modification to lower the active, the energy?
You are asking two different. There are two different places where we talked about covalent modification. One was regulation of enzymes. The other is enzyme mechanism. So you are talking about covalent catalysis.
Yeah.
Not the covalent modification for regulation. So let me answer both. It doesn't matter which one you are asking. So regulation can be by allosteric regulation, by binding of two things. The inhibitor binds to the enzyme and inhibits or activates it. That's allosteric regulation. It can be by covalent modification, which is usually a phosphate. So a phosphate will be added to one of the amino acid, important amino acid at the active site. And that way the enzyme will either be made inactive or active. There are both examples, so there is no point in memorizing these. Some enzymes are activated by phosphorylation, some are activated by dephosphorylation. So that is the covalent modification that regulates enzyme activity. and the third one was of gene expression. The other question that is possibly your question is about covalent catalysis, which means how enzymes speed up a reaction. And we talked about proximity, then acid-base catalysis, binding to the transition state, and the most important one is covalent catalysis. So if you have energy diagram that requires a high activation energy. So let's say without enzyme it requires a high activation energy.
No, so I lost the script. So no. Can you start it back?
So without enzyme, this is a high activation energy, and so the reaction doesn't happen. The way the enzyme can make it happen is to break up this one step into two steps. So it will first react to your substrate with the enzyme and form an intermediate, and then the intermediate gives you the product. So it is forming a covalent bond with the enzyme.
That's how it's here.
And that way it is coming close to the transition state. And so now the energy of activation, with this one I haven't really drawn it correctly, so I need to bring it down here. And then you go this way. So this much will be the activation energy with the enzyme, and this big one is the activation energy without enzyme. And so now the activation energy is less because of the covalent bond formed between the enzyme and the substrate, or part of the substrate. So one example of that would be all the kinases, for example hexokinase. ATP adds a phosphate to glucose to give you glucose phosphate. So this enzyme, this reaction without an enzyme will be impossible to do, because if you take ATP and mix it with glucose, it will stay like that forever. Because this reaction has a very high activation energy. So what the enzyme does is it breaks it up into two steps. So first the enzyme binds to ATP and gives you enzyme phosphate plus ATP. So that means the phosphate forms a bond, a covalent bond with the enzyme. And that's where it is closer to the transition state. So this is your enzyme phosphate. And then in the next step, enzyme phosphate reacts with the glucose, give you glucose phosphate. Alright, so this reaction, the enzyme makes it possible by forming a covalent bond that has energy closer to the transition state, and that increases the energy of activation. So this type of mechanism is called a covalent catalysis.
EP decreases the energy required to start it, but then it gives you a closer.
Yes, anyone else has any other question?
Can you briefly go over isoelectric?
Isoelectric point is what? Is it defined as? Defined as the pH at which the molecule will have a net zero charge. Right, so isoelectric point, the term applies usually when you have one end of the molecule has a positive charge, another end of the molecule can have a negative charge, and there will be different amounts of them. At a certain pH, there will be equal amounts of them. That will be the isoelectric point. The reference here is mostly to the amino acids, which have a carboxyl group and an amino group. So it has an amino group and carboxyl group. The different forms can be a positive charge on this one and a negative charge on this one. So if you are starting at a low pH, that low pH will be lower than the pK of this one. So this will have a positive charge already. So very low pH, lower than 2, let's say. That means lower than the pK of this one. So only this one will be charged, this is not charged, so this has a positive charge. As you increase the pH, gradually this will also ionize. And then you have a plus and a minus charge. So at what pH will this happen? That all molecules will be having a plus and minus charge. As you increase the pH more, then this proton will be lost, so you now get NH2. So this has a negative charge only. So somewhere in between this step and this step, you will have all the molecules in this form. So it has to be above the first pKa, below the second pKa. And exactly the middle will be the isolated point, so it will be half or average of the pKa values where you will have all the molecules as plus or minus. So the other definition of isolated point is that the molecule doesn't move to either positive or negative electrons at the isolated point. Yes?
Yeah, so on this topic, I just wanted to ask a question. So let's say we have 3 pKa values. What's, I would say, like the quickest or easiest way to know which of those 3 will I use to calculate PI?
If you have 2 carboxyl groups, it will be the average of the 2 carboxyl groups. If you have 2 amino groups, it will be the average of the 2 amino groups.
For something like
That's the easy way to remember. Yes.
something like histidine, would
Yes.
it be the average of the two so
Amino groups, yes, because it's dealing with pieces.
Then you would know that this is the section.
How about from tyrosine? I don't
The only 3 basic amino
like a
acids
lot
are
of
H, K, and
tyrosine I
R.
was looking at.
Histidine.
Doesn't follow that rule.
K, I don't know what K is.
Tyrosine, the high pK.
What
What is the pK of
and that's
tyrosine?
whatever
And
R
what's
is,
up?
not tryptophan.
As an acid. Right, so you have to, if it's working as an acid, then you have to take the average of the 2 acids. Acid groups. Yes. Yeah.
for molecular lysis, what does it mean by activation of the
That's true for all the synthesis reactions. Whenever you are synthesizing something, the general idea is that if the energy of the product is here and the energy of the reactant is here, you're going to a higher energy level. And let's say this is equal to about 1 ATP equivalent, the difference. So you can expect that in the opposite pathway, when you came from here to here, you probably made 1 ATP. When you go from here to here, providing 1 ATP is not sufficient. As I said, if this is an irreversible step, going from here to here is usually also an irreversible step. So how do you make that happen to an irreversible step? Most cases what happens is you activate this to a higher energy level and then you come down so that this step is an irreversible. So that means you have to provide more energy in this direction than the energy that you get in the opposite direction. That's what we saw in gluconeogenesis also. In the last step of glycolysis, you make 1 ATP, but when you go in the reverse direction from pyruvate to pyruvate, you need 2 ATP. Always need more ATP in the opposite direction because reaction must be made irreversible in both steps. So all biosynthesis reaction will require you to activate your substance. Just like here, you are activating the pyruvate to oxaloate. Same way for glycogen synthesis also you need to activate. The glucose 1-phosphate is already an activated compound, right? It has a phosphate bond to glucose, so it is a high energy compound, but that is not high enough. So you need to put another energy into that, and that's why you use what? What is used to activate it? You use UTP to form UTP glucose. Most of the time, the U and the A and the G, these are equal amount of energy. And systems have evolved to use one or the other. So most of the time, there's no point in memorizing which one uses GTP because maybe humans will use GTP and plants will use ATP and another species uses something else. Of all these, this step, particular step, may be asked in your exams and even in your board because people are fascinated by this step that it is a UTP that is used for activating glycogen synthesis. So please remember that it is a UTP for this step, not ATP, not GTP. And then the reason is that U actually becomes part of the product. The product is glucose with a UDP. So it is UDP glucose. If that is the name of the product, you should also know that UTP is used to provide the energy. In other cases, as you will see, sometimes ATP is used. Humans may use ATP and other species use GTP. So those are not really worth memorizing. You can look it up all the time. Just know that there will be an energy needed or energy made in those steps. Yes.
How does the general reaction of an enzyme catalyzed reaction help define a diffusion controlled enzyme?
Oh, it's only because
I was getting this. I gave this question.
it's only because the reactions that are the ones that are
I didn't hear the question. Yeah, let's go. Post
Alright, so this is a general equation for enzyme reaction. The second step is not equilibrium. Why is it not equilibrium? Because you are doing initial rate. That means you are looking at the reaction in the first few minutes for a short time only. So you don't have the second one as a irreversible, as an equilibrium step. So this K2 is the slower step than the K1, K-1, which depend on the rate of diffusion. And so K2 is also called the K-cat. And what is the question?
How does this equation help define a diffusion
The diffusion controlled enzyme type. So since K2 is the slower step, the enzymes will adjust or evolve to have different K2 values. Some will be fast enzymes, some will be slow enzymes. And if it is a fast enzyme, it will be, instead of 10, it will be 100 or 1,000 or a million. So there is a limit to how high it can go. Then that limit is the rate of diffusion, because this is the slower step. If you keep on increasing this, there will come a point when it will be equal to the diffusion. And the rate of enzyme reaction, even if it is faster than the diffusion, your overall rate is not going to be that, because then the rate will be controlled by the rate of diffusion. So those enzymes that have evolved to have the highest possible K2, which is equal to the rate of diffusion, are called the diffusion controlled enzymes. That means there is no point in evolving better than that, because it will be restricted by how fast the two molecules can come together, which is the rate of diffusion.
So K1 is the rate of diffusion.
K1 is the rate of diffusion, so when K2 becomes same as K1, those enzymes are called diffusion controlled enzymes. Or the enzyme may actually have a higher K2, but there's no help having a higher K2, the rate will still be K1, that is the diffusion controlled enzyme. Alright, yes.
Is it equal to K1 or to KM?
K1.
K1, not KM. KM is a concentration, not a rate. Alright?